All right, thanks for returning. And today we're going to talk about section 3.3, which are graphs of basic functions, which you really do need to, you really should, you should be able to recognize them. So when I say that, I kind of mean you should really memorize what they look like. Okay. I mean, I hate for you to memorize things, but you do want to know, like if you have a function that you might want to know what the shape of it is. So that's basically what we'll talk about. And then we'll talk about piecewise functions. So sketching the graph of basic functions. Sketching the graphs of basic functions with restricted domains, and then piecewise functions. So I'll show you basically what I mean. Constant function. If ever you have f of x equals b or y equals 3, same kind of thing, you're always going to have, remember, if you have the slope-intercept form of a line, which is y equals mx plus b, if this is what they're saying, if m equals 0, then we have no slope. Slope is the measure of the incline, so we have no incline, so which means it's horizontal, which means this goes to 0, and I just get y equals b, okay? And that's a constant function. Then we have what we call the identity function. It has a slope of 1, and it has a y-intercept of 0. So remember, y equals mx plus b. So for a line that is y equals x, this is basically f of x equals x or y equals x, we have a slope of 1, and there is no y-intercept because it's 0, it goes through the origin. Okay, so this is a linear function. Squared, again, I've said it, but I know we haven't taught it yet, but anything that's squared always looks like a parabola. This is called a parabola. And it opens up y equals x squared or f of x equals x squared, and it always looks like that. Even if I have other terms after it, it's still going to look like a parabola. It's just not going to be centered right there at the origin. Cubic functions, x cubed always looks like this. If you plug in a value, and it's an odd function, if you plug in a value here, it should be at this x. If this is minus that, whatever that x is, you have a matching one here. Cubic functions are odd, and actually, I should say these are even, these are odd. These are, well, that's symmetric around the y-axis. It is not, so this is an even function. It's not an odd function. This is what a cubic function looks like. If you want to graph x cubed, it looks like that. Absolute values always look like a V. They could be placed anywhere on the axis, but the main thing is they look like a V, because if I just took y equals x, it would come down this way, right? But absolute value makes every value positive. So it takes this blue part right here, and it flips it and makes it positive. So it always looks like a V. This is what a square root function looks like. It just has this shape because, so for example, if I have here 1, 1, it starts out there, but the next one is 2. 2 is going to be farther away. Well, actually, so the next place that I can take the square root of something is 4. So let's say this is 2. So that would make this 4, and that would be my 0.24. And then I have 2 and 3 in the middle of that, right? So the x's are getting large more quickly than the y's, and that's what's happening. That's why it's kind of sloping out like that. Okay, the next one I would get would be 3, but that's where x equals 9. So it would be out here, right? And that's what the square root function looks like. The cube root looks a lot like the square root, except remember, we talked about this with root functions, is that it can also be negative. Square roots cannot be negative, x can't be negative, so I always start here at 0. But cube roots can be positive or negative, so it has almost the same shape as the cubed, only it goes on its side. Okay, similar but different. And that's why this can have negative values, whereas squares cannot have negative values. So these almost look the same, but if I were to flip this negative part up, it would look a lot like a parabola, right? Because they're similar. So that's what x cubed looks like. It looks like an x squared almost, but it also has the tail in the negative direction. And then 1 over x, this is our reciprocal function, and it looks like this. And we haven't learned again about asymptotes, but it never touches either the x or the y-axis. And we'll actually use this function when we talk about asymptotes. This is a nice function to use. And then we have, this is called the greatest integer function, and it has that symbol. And basically what it says is, let's say this is 1, 2, 3. So if I'm between 0 and 1, if x is anywhere between 0 and 1, well, we haven't gotten to 1 yet. So the greatest integer is 0. And that's why we have that line. And now we say if x is, let's say x equals 1.5 or anything between 1 and 2, the greatest integer of x, well, the greatest integer is 1, right? Because we haven't made it to 2 yet. So that's why we have these constant lines. But when we get to the next value of 2, it jumps. This is 1, this is 2. Okay, so that's basically how greatest integer function works. So sketch the function for x is greater than 1. Actually, let's actually do it. I don't want to just, so here. Oh, there it is. So that's what it looks like, but let's cut it and let's do our own. So here's 1, and let's just make some lines. 2, 3, 4, 5, 6, 2, 3. I'm not going to need to go up that high, right? And we know that y can only be positive because the square root of x can only be a positive number. So I don't have to worry about what's below the x-axis. So let's sketch the graph for x is greater than or equal to 1. Well, when x is 1, square root of 1 is 1, right? And I don't really want to figure out what square root of 2 is, square root of 3, even though I know it's like 1.4 is the square root of 2 and 1.7 approximately is the square root of 3. So those are just hard to graph, but let's say we do that. Well, we do know the square root of 4 is 2, so that's the easy one. And really, until I get to 9, I can't really graph the 3-point, right? So 7, 8, 9. And just like I said before, it's increasing, but at a very slow rate, right? So it's kind of having this, like, it's not straight, it's not a straight line, but it's sloping up really slowly. So let's see where the square root is here. So you see how it's sloping up very slowly, but it is still going up. Okay. Let's see. Where did I? Nope. Sorry about that. I just have to find where I was. Yeah, here's where I was. So that's it. I mean, there's really nothing more to say except pick some points and you know what it should look like. So you really need to remember at least what it should look like, okay? Because if I say sketch the graph and I have no numbers, all I really want you to do is go bump, bump, and then like that, and say this is the square root. I'll believe you. It's a sketch. It's not a graph. It's not to scale, but it is a sketch. So that's what I need you to be able to do, is be able to say, this is what it looks like. All right, so the last thing we're going to talk about is piecewise functions. And piecewise functions are functions that have more than one piece, or they're defined by more than one rule. So here we say functions that are defined by a rule that has more than one piece, okay? The absolute value function can be defined by a rule that has two different pieces. Because if I want to know what the absolute value is, well, if x is greater than or equal to 0, then it's just going to be whatever x is, right? If x is 5, then it's 5, so on. But if x is negative 5, well, if I put a negative 5 in for x here, then what's really happening is I'm saying a negative of my negative, because it's always going to be positive. So that's why it's saying there's two different pieces. If x is great, so we read it like this. Here's my y value. If x is greater than or equal to 0, I say it's whatever x was. But if x is less than 0, then I say it's the negative of whatever x was. So let's do an example. So 1, as we can see from here, 1 is going to be the dividing point of these two pieces, right? So I want to know, for example, when x is 1, which one of these am I choosing? Well, I'm going to have to choose this, because this is including 1 and this is not including 1. So if I want to know what y is when x equals 1, I have to look at this bottom function. So I plug in, here, let me see how I want to write this. So here's x, here's f of x. When x equals 1, then I use the function. I know how to do this. Let's do it like this. So the function I use is 1 minus x. And so I plug in 1 and I get y is 0. So I have a point when x equals 1, y equals 0. That might work. Okay. When x equals 2, I still use 1 minus x. So when x equals 2, I get negative 1. So there's my other point. And this is a linear function because this is the same as minus x plus 1, right? And I have a slope of negative 1, which it looks like I'm going to have a slope of negative 1 because I am going down from here to here. And it continues on because it's when x is greater than, so it just goes on forever in that direction. Okay? And that's really the basics of anything where x is greater than or equal to 1. It's going to always go to this bottom part of the function because that's where x is defined. But what if I say x is less than 1? So let's say x is equal to 0. Now I have to use this function because 0 is less than 1. So now I'm using x squared, which is again 0. So when x equals 0, I have this point 0, 0, right? When x equals negative 1, let's see what happens. So when x equals -1, again, I'm using x squared, and -1 squared is 1. So when x equals -1, y equals 1. So I have this point. Now, I know this is going to sound weird, but we really need to figure out what happens when x is 1 if I use the top. It's not going to include 1, but we're going to plug it in anyway. So let's see, I'll use red for this one because this is kind of the weird one. I know right now that these two are connecting, and I also know it's a parabola. So because it's x squared, I know it's going to like go up like that, like a parabola. Probably not that quickly. Here, let me do better. So let's say when it's -2, it's going to be 4, right? Because we're going to use x squared. So this is 4. So 1, 2, 3, 4. So I have this point here. And so now I can kind of better see what it's not good either. So it's kind of going to go like this. Okay. The only problem is I don't know what's happening between 0 and 1 because I've just picked whole numbers, right? So what I want to do is I want to pick 1 again because that's the transition point, right? It's doing something when it's greater than or equal to 1. It's doing something when it's less than 1. So I need to go all the way to 1. And this time I'm going to plug it into x squared. And when I do, I see that it's going to equal 1. So I have this point at 1, but it's not a closed circle, is it? It's going to be an open circle because it doesn't include the value at 1. But now I know this graph continues up like this. Well, it doesn't have an arrow. It continues up like this till it gets to 1, and then we have an open circle there because it doesn't include 1. Okay, so I do need to figure out what it would be if it included 1, but then I make it an open circle. And we can kind of see that we have this parabola, which is x squared when x is less than 1, and I have this straight line which has a slope of -1. And it has a y-intercept of +1, which if I did continue this, we could kind of see that that's where it would go. So this is how you sketch a piecewise function and how you evaluate a piecewise function. And oh, look, there's a much prettier picture of exactly what we just did. So if I look at what we graphed, and it looks very much like this, except this one is, of course, much prettier. Now let's find the rule that describes the following piecewise function. Find a rule. So what are we going to do? I think we need to just graph it. So let's see. All right, so let's see what we got. So let's put our graph up. And we have 3 different transition points, right? We have x is greater than 1. So let's put a 1 here because we really need to know what's happening around 1 because it's changing. And then this is between -2 and 1. So let's go -1, -2. And the top one goes between -2 and -3. It doesn't continue into negative infinity because I don't have anything defined at -4 or -5, right? So we don't go past -3. So if we were to, let's do the same thing with our x and y. I'm not sure if that's helpful or not, but if it is, I'm going to do it. Okay, so let's start at the top. So let's pick a number between -2 and -3. Actually, let's pick both -2 and -3. Even though they're going to be open circles, I really want to know what those values are. So when x equals -3, I'm going to use the top function because I need to know what's happening. And that would be -3 times -3, which is +9 minus 6. So I get a +3. So 1, 2, 3, which means at -3, I get +3, but it's an open circle because it does not include -3. And then -2, I know if I wanted to find exactly what it is, then I would have to go to the middle. But I want to know what happens when this is negative, when the top function is -2. So I plug it in, I get 6 minus 6, and I get 0. So that means that the other end, actually, let me do those in red. So the other end is at -2, 0. And also we can see it's linear because we can see the function is -3x minus 6, which is a linear function. So that means it's just a line that connects those 2 points. Okay, and they're both open circles at the end. And these are from the top equation. Okay, I'll do them all in different colors. Then we have the middle part, right? So we have the middle part, which is 2. And that does include -2. So when x equals, so this is for the middle, when x equals between -2 and 1, including both endpoints, my y value is 2. So at -2, at -1, at 0, and at 1, all my values are 2 because I just used 2 for y. So between there and 1, and again, because it's less than or equal, it has the equal sign, I include those points, and this is just a constant function, just a straight up cross line, okay? And then the last thing I do, which I don't have room for, but I'll try to do it anyway. This is the bottom. So now we're talking about when x is greater than 1, but I still want to see what number it would be if I plugged 1 in. And I plug 1 in and I get -1 plus 2 is 1. So I know that that next one is actually going to start here at 1. When x is 1, y is 1. Oh, actually, that's 2. So it's going to start here, but it's open at 1. And it's got a slope of -1 and a y-intercept of 2. So we know that it's going to be sloping down. And and it's a line. So let's put in x is 2. When x is 2, y is 0. And it's going on forever, right? It's not telling me an endpoint. So I'm just going to connect these 2 lines, and this is going to go on forever. And that's how we graph a piecewise function. I don't know why it says find the rule. I think it means find the graph. These are the rules over here over here are the rules for this piecewise function. This is the graph, and I think the next slide has a prettier graph, which looks like our graph, right? So this is exactly how you plot piecewise functions. If I asked you to tell me what is y when x equals, let me think of a good one, -2. Well, when x equals -2, well, I don't use this one because that doesn't include -2. And I don't use this one because x is not -2. I have to use this one when x is -2 because this middle one includes -2. So my answer would be 2. So when I want to evaluate, I definitely have to only use the piece that I need. But if you notice, I also had to use the transition points to find out where my graph would start and where my graph would end. So I did plug in numbers to the places where they weren't true, but I still put open circles there. So hopefully all of this made sense and you understand about piecewise functions. And if you don't, please feel free to ask me. I'm very happy to help. All right, have a good day.